Hi, my name is Pracheth and this video is going to be all about edge detection. I'm going to show you how to make edge detector using gates, transistor and using microcontrollers. So let's get started. So whenever there is a state change from 0 to 1 or 1 to 0, it's called as an edge. When there is a state change from 1 to 0, it's called as a falling edge. When there is a state change from 0 to 1, it's called as a rising edge. So here I have a system which is generating a square wave oscillating back and forth between 1 and 0. Okay. And when there is a state change from 1 to 0, the negative edge detector's output is a voltage spike. And when there is a state change from 0 to 1, this positive edge detector's output is a voltage spike here. In this way, a negative edge detector responds when there is a change from high to low. So in that event, it will give a voltage spike at the output, and this spike can be used to trigger a multivibrator or a latch which can start a motor. Okay, so it's very useful in control systems and digital systems. So now let's see how to make this edge detectors using gates. So this is the circuit diagram of a positive edge detector. This for a negative edge detector. So this positive edge detector works because there is a propagation delay in the NOT gate. So if you give 1 here, it's supposed to be 0 here, right? Because it's inverting. But it doesn't instantly become 0. When you give 1 here, it's 1 here. The previous state is still retained and gradually it becomes 0. Because this doesn't goes here instantly. There is a lag. And how that propagation delay is useful in positive edge detector we are going to see in the simulator. So now let's make these two circuits in the simulator and see the waveforms. It will be more clear. So now let's make a positive edge detector on this simulator app called Every Circuit. I'm using this app because the output I get here is most of the time same as the practical output. So to make a positive edge detector I require an AND gate and a NOT gate, and also I will require logic source. So this logic source output 0 volts and 5 volts. 0 is for 0 and 5 volts is for 1. So we'll connect it to this AND gate. So to show you how an AND gate works, we'll connect one bulb at the output. We'll start the simulation. So when both the input is 0, the output is 0. But if one of the input is 1, the output is still 0. If both of them are 1, then the output is 1. So this bulb's forward voltage is not set to 5 volts. So both the inputs must be 1, then only the output turns on. Otherwise it's off. Okay. Now let's see how to make a edge detector. So it's very easy. You just add a NOT gate to one of the inputs and you short this. So this is a positive edge detector. So what do you think? What will be the output? 0 is on this input and this NOT gate is inverting. So it's 1 here. So 1 0, it's 0 here, right? So what will be the output when it will be 1? 1 is going here. It will be inverted 0. So 0 1, it will be still 0. Let's see what happens. So here it's 1. You can see it red. Okay. So I'll change the input to 1. You can see that the bulb was turned on for a short period of time. That's because of the propagation delay of this NOT gate. So right now it's 100 microsecond. Let's increase it to 1 millisecond. But in reality, the propagation delay is in nanoseconds. So whenever there is a transition from 0 to 1, right now it's 1 here. But if there's a transition from 0 to 1, this becomes 1, but this 1 doesn't turn to 0 instantly. That's why the output stays high and it gradually becomes 0. So when it becomes 0 completely, the output turns off. And in this way, we get a voltage spike at the output when there's a transition from 0 to 1. Let's see the output waveforms. And whenever there is a transition from 0 to 1, you can see the voltage spike. But the voltage spike is not of 5 volts. its maximum is 2.18 volts. So the peak voltage here, the spike, is not going to 5 volts. Why it's like that? Let us see. So I will mark this input also, and I'll see the waveform. So whenever there is a transition from 0 to 1, let's see the waveform. So look at the green waveform when there is a transition from 0 to 1, and look at the orange waveform, which is the output of a NOT gate. It's gradually decreasing to 0. So up till this point, okay, it sees 1. That's why the voltage is rising. But after this point, it starts to drop. And after this point, the AND gate sees 0 here, 0 at the input. And the voltage starts to drop. So this was a positive edge detector. Let's make a negative edge detector. I will use one more NOT gate. So adding one more NOT gate here will convert it to a negative edge detector. So let's connect a bulb at the output. So let's see how this negative edge detector works. I will start the simulation. So whenever there is a transition from 1 to 0, which is a falling edge, you will see a peak at the output. So you can see that this pulse, the output pulse, is not coming instantly. There is a delay after the falling edge. This delay is due to the added propagation delay of this NOT gate. But it doesn't affect in practical, it's in nanoseconds. So in this way we saw how to make a negative and positive edge detector using AND gate and NOT gate. So now let's see how to make it using single transistor. So this is the circuit diagram of a single transistor positive edge detector. Instead of a square wave, I am using a switch here. So pressing the switch will cause the voltage to rise at this node, and releasing the switch will drop the voltage. So let me explain you how this works. So first you need to understand when a transistor turns on. So this is a NPN transistor BC547. It will turn on when it will see current is flowing towards the base. Okay. So when the current flow is from the positive to negative, then this transistor will turn on and there will be a current flow from the collector to the emitter. And this LED will glow. So let's understand what happens when the switch is pressed and voltage rises. So at the rising edge, so press the switch. You can see that the LED glows for a short period of time. So what happens here is when I press the switch, the capacitor gets positive 5 volts and negative. So it starts to charge. And while the time it's charging, okay, the current flow is in this direction. The transistor turns on, the LED turns on, but as the capacitor starts to charge, okay, the current across it starts to drop, which gradually turns off the transistor and the LED turns off. And in this way you get a voltage spike at the output. So this is a negative voltage spike as this transistor is NPN, it switches ground. So normally it's 5 volts here, but when it turns on, okay, there will be a voltage drop. So you will get a negative voltage spike here, and I will press the switch, and the switch is still pressed, okay. The capacitor is fully charged, but the current is 0 now. That's why the transistor is off. So I can keep the switch pressed and the LED is still off. But when I release the switch, nothing happens. That's because when I release the switch, the direction of the current flow is in this way. So the capacitor starts to discharge through this resistor. The direction of the current flow is in this way, going away from the base. That's why the transistor is turned off. The LED stays off when we release the switch. Okay, and in this way the positive edge detector works. So to make a transition from a positive edge detector to negative edge detector, all you need to do is change the switch position from here to here, okay, such that now when you press the switch, okay, the capacitor will discharge, and when you will release the switch, it will charge. So when it will charge, the LED will glow and you will get a negative voltage spike at the output when you will release the switch. That means at the falling edge. Let's change the switch position. So all I need to do is just connect this switch to ground. So here I have a negative edge detector. So when I will press the switch, nothing happens, but when I will release the switch, there is a negative voltage spike and the LED flashes. So in this way you saw how to make a positive and negative edge detector using single NPN transistor BC547. Now let's see how to implement edge detection in microcontrollers. So here is the code written for edge detection in Arduino IDE. I'm going to upload it in ESP8266. So I'm implementing edge detection on GPIO 10 in ESP8266. That's why I've connected switch on pin 10. I've connected one LED on GPIO 16 because I want this LED to blink when edge is detected. The switch state variable is to store the state of the switch, so whether it's high or low. So when the switch is not pressed, it's pulled high so that the value is 1. That's why I've kept the switch last state variable is equal to 1. Okay. In the void setup, I'm defining LED as output and switch as input. In the loop, I am reading the switch state, okay, and storing it in a switch state variable. So whatever the state high or low is stored in the SWST variable. So initially it's high, okay. So switch state is equal to switch last state because this is 1. 1 is high. So this condition is false, right? And this if statement is not executed. Then it goes here and here switch last state is equal to switch state. This means this line makes this condition false. So next time when this runs, next time when this loop runs, it will read the pin. It's the same and it will see whether this condition is true or false. It's false, so this lines will not get executed. And in this way, whenever there is a switch state detected, that means whenever we press the switch state changes from 0 to 1 or 1 to 0, then only this condition will become true. But as soon as it reaches here, this condition becomes false. So next time when this loop runs, it sees that the condition is false and these lines are not repeated. Whenever there is a state change, either from 1 to 0 or 0 to 1, whatever written inside this if will run only once. So I want the LED to blink when there is a state change. So I will write here digital write LED comma high and delay of 200. So now let's upload this code. So yes, the code is uploaded and when I will press the switch, you can see that the LED blinks and the switch is kept pressed, and now I will release it, it will blink again. So it's detecting the falling edge, and when I release it, it's again detecting the rising edge. So in this way, it's a state change detector. So in this way, both the edges are detected, positive and negative. So what if you want only the rising and falling edge? So for that, let's see what is to be done. So these lines of code were executed when there was a state change either from 1 to 0 or 0 to 1. So what if you want to make a rising edge detection? So for that, all you need to do is write here one condition: if SWST is equal to high, and inside this condition you have to write this LED blink code. So this means that whenever there is a transition and switch state is equal to high, that means it went from 0 to 1, then only this lines of code will get executed and the LED will blink. So what if you want a falling edge? So here you have to write low for falling edge. That means there was a state change, there's a transition from high to low. So this will detect a falling edge, and writing here high will detect a rising edge. Now let's make it low because I want it for the falling edge. So now let's upload this code. So the code is uploaded for falling edge detector. Now when I press the switch, the pin 10 will be pulled low and this LED will blink. and when I release the switch nothing will happen. So for the falling edge only the LED blinks. So in this way we saw how to make a falling edge and rising edge detector using AND gate, transistor and microcontroller. I hope you found this video useful. Like and subscribe to my channel. Thanks for watching.